Okay guys, in this video lesson we're going to start talking about force and how it affects things as you move things in a circular path. Okay, so first thing we want to make sure that we're aware of is that we're not changing the concept of force at all. Force still is applied by taking the mass of the substance times its acceleration. Okay, so if you still apply a force, even though we're going circular, we still can work with this idea that there's going to be a certain amount of mass that we're applying that force to, and it's going to create an acceleration, still going to be in newtons. Okay. Now, this also holds true that force is still in the same direction as the acceleration. Okay, if you remember in a previous slide, we talked about how the acceleration is moving inward during circular motion, which is actually perpendicular to the movement in this case because we're bound by inertia pulling it out and the force pulling it in. So when you have the combination of the inertia wanting to move tangent to the circle and the force wanting to pull it inward for that circle, what happens is we get this resulting circular motion. Okay, so the acceleration is constantly inwards. Okay, with the center-seeking acceleration, that means the force must also be center-seeking. Okay, that force that we call it, the name we give to that force is centripetal force. Okay, that force can be generated through tension on a string. It can be generated through, let's say, some sort of metal ring and a ball is inside of that. It can be generated through friction. When you turn the tires of your car and you go around a curve on your car. It can be generated through, let's say, a hand and an arm in a baseball or softball pitch. So anytime there's something that allows that force to be pulling things inward as you have momentum, which is related back to our inertia of our object that wants to move tangent or wants to move in a straight line. Okay, so the combination of this force and inertia causes a constant circular motion. All right. Now, a lot of times students talk about when we take a corner though or a curve, it feels like we're being pulled to the outside. Okay, or it feels like we're being pushed outwards, and often people use a term that's called centrifugal force on that, and that term is actually a false term. Okay, so there is no such thing as centrifugal or centrifugal force, however you want to pronounce that word. Okay, so that force really does not exist. It's actually kind of more like a mythological type of force that we incorrectly use to describe what's really going on. Okay, so let's talk about what's really going on there instead. So to do that, we want to draw a curve. Okay, so if we imagine this is a pathway and we are moving along this pathway on a straight line, and then at some point in time we make a curve. Okay, when that happens, if we do these black lines that tick off, let's say 1 second at a time, we can take a look at what goes on. Well, once we start curving, centripetal force, PET, centripetal force, PET, pulls us inwards, okay, as we go around this curve. So something is causing it. Let's say this is a car, and the tires of the car create friction, and that friction is going to pull us so we stay inwards on that stuff, okay? Or maybe, you're driving along and you get attached to a string, and the string starts to whip you around a corner, okay? Something happens to make you curve, right? Now, as you move along, okay, if you have an object that's in the car or as part of this, it wants to move in a straight line, okay? So if we take a look, and here's our object, if we draw a straight line through all the yellow dots, that's the pathway something wants to move at, okay? We know that's the case because of our first law of motion. We said that everything in motion wants to stay in motion, meaning it wants to not change or it doesn't want to accelerate or turn. So because of its inertia, all right, it wants to move in a straight pathway. Okay, so it comes down to inertia for us. It wants to move in a straight pathway because of its inertia. It doesn't want to push outwards. Okay, we perceive it that way, but it really isn't pushing outwards. What's happening is the object, let's say we're in a car, the car turns left. So because we're part of the car at this point and we're turning left, we perceive that our bodies are being pulled outwards. The reality is our bodies want to move straight. Okay, so it wants to move in a straight line, and instead of curving with the car, that feeling we get is because of the inertia that we have wanting us to move in a straight line. Okay, so that's kind of where it comes from. You ever want to test this out? Take a pen or something that can slide, put it on the dash of your car, and then even if you take a normal corner, that object will slide across your dash. And again, it looks like it's moving to the right if you take a left-hand turn, but really, if you pay attention to it, it's actually moving straight and the car is turning left underneath it. And there's just not enough friction to hold it on the dash, okay? I wouldn't do that with your cell phone, but something that you know can't break. It's a neat little thing to show, and it works every single time. It'll slide right across the dash of your car as long as your dash is relatively flat. And it's not because it's moving right, it's because it's going straight and the car is turning left. So kind of show that with this diagram here. All right. Now, once the object, hits the side of or the end of that window of the car or the dash, or once you tighten up the muscles in your body to stop yourself from sliding, then you're bound by the same centripetal force that is pulling on the whole object, which means you will now continue to move along that curved path. But it's going to constantly make you feel like you're being pulled outwards because your inertia wants to go straight and centripetal force is pulling you inwards. Okay? So that's kind of how it works with inertia. So putting all that stuff together, what we can go back to is how do we build a formula for this? Okay? So force equals mass times acceleration. We know that. This is now our centripetal force. And what we want to do is we want to take this idea of acceleration, and we solved for acceleration earlier in this unit in terms of how do we do centripetal acceleration. So we need to put those things together. So let's insert values for centripetal acceleration here, combine it with mass to be able to find a force. If we do that, we get these two equations, okay? We get this idea that force that is centripetal will be mass times the velocity squared divided by radius. Now, if you recall, velocity squared divided by radius, that's just the acceleration. So really saying mass times acceleration here. We also had an equation for acceleration that was 4 pi squared r times period squared. So if we take all of that times the mass, it's another way we can find our centripetal force. So either of these equations work. The reason why we give you both is because in certain cases, you know the tangential velocity, you know the radius. In other scenarios, you might know the mass, the radius, and the period. So if you notice, we either need to give you velocity or give you period to make this thing work. You got to have one of these two things, otherwise you can't find the force of your object. Okay? So that's our equation. Now, let's do a little practice on it, all right? So a female hammer thrower uses a 1.22 meter chain to toss a 4 kilogram ball. If she completes one full rotation in 0.232 seconds, let's find the following. Okay? Velocity of the hammer releases it, centripetal acceleration, and then tension on the chain. So tension would be that centripetal force now. Okay? So we've done this before. This is the new piece of the puzzle. Okay? So go ahead and pause the video here, and then try to work it out. And then when you're ready, hit play again, and we'll show you the answer. Okay? Hopefully you had a chance to pause it and work it out. So now let's take a look at how this thing works out for us. All right? Going back to our problem, our radius is 1.22 meters. We have a mass of 4.00 kilograms, and our period is 0.232 seconds. Okay? To find that velocity, we go back to our first equation, which is our circumference divided by the period. So we plug in our numbers, and we should get 33.0 meters per second. Okay? To find the acceleration, because we know the velocity now, I use this equation. So I took my velocity to the tangent squared divided by my radius, and I was able to get this acceleration. Notice how I didn't use the rounded number here. I used an unrounded number in my math because this number might cause a rounding error if I do that. Okay? Labeled in meters per second squared. Finally, the new stuff. Okay? So the tension. I could have really used any equation to solve this. I could have used both of them for force. I chose to use this one because I thought it was the simpler of the two. So I know my mass is 4 kilograms. I know that my tangential velocity from the very first problem was 33.041. I had to square that value. And then I'm going to divide that by the radius. And if I do that, I get 3,580 newtons. Okay? So again, one little reminder, when we do circular motion, it's pretty common we get big accelerations and big amounts of force here. So it's a little different than in our previous unit, where our accelerations were typically under 10 and our forces were typically under 1,000. Now in this case, we're going to see bigger numbers here. So that's pretty common, and that should look okay to you. All right. Let's do another one. Now we're going to do the men's hammer throw. Same radius, okay? However, the ball at the end they use for the men is much, much heavier than the female one. So it's 7.26 kilograms. It's almost double that. In this case, we know the force that is able to be generated. So it's 4,010 newtons, or 4.10 times 10 to the third newtons of force. Okay. So we know the force now, so let's go back and kind of flip the problem. What's your period, what's your acceleration, and what's the velocity? So notice how we're using force now to find other things, okay? So once again, go ahead and pause the video, and then once you're done working it out or doing your best at it, we can hit play, and I'll show you how to do it. Okay, now that you've paused the video, let's take a look at our answers. So again, we want to list out what we have. So we have our radius, we have our mass, and we have our force. Okay. The period of rotation, probably the hardest one mathematically to solve for. We need to get the period, which is kind of buried in the denominator here, and it's squared. So first thing you want to do is get your period out of your denominator. So I moved the period over here, and I brought force down. And then because it was squared, I square rooted the resulting of that. So I end up having my period equals the square root of 4 pi squared mr over my force. Okay. Now that I've rearranged it, I can plug my numbers in. I have my mass here, I have my radius here, I have my force here. Don't forget to square the pi that's inside of here. Okay. Square root the whole thing when you're done, and you end up with a 0.292 seconds. What's our acceleration? This one probably is one of the easiest calculations. We know the mass, we know the force, we just got to find acceleration. So rearranging it, plugging in our force and our mass, and we get 565 meters per second squared. Okay? And then finally, the velocity. So again, we know our force, we know our mass, we know our radius. So we're going to rearrange this, and then we're going to square root it so we can get just the velocity to the tangent. So put our force in, put our radius in, put our mass in, and we get 26.2 meters per second. All right, guys, that ends this video lesson. If you have more questions, please let me know in class. Thank you.